Hello and welcome to our calculus notes for section 4.4c, the definite integral as a function of x, and the second fundamental theorem of calculus. So let's start off with the definite integral as a function of x, and we'll try to explain this here. So we'll see. We want to talk about the definite integral as a number. And so in this case, if you look at the a and the b here, we have the definite integral from a to b of a function of x with respect to x. So in this case, the a and the b are actually constants, and they're x values. Okay, so this right here is a constant, and so is the a, also a constant. Okay, and it turns out that these are x values because we're using them with the function of x with respect to x. Now, when you calculate this, you actually get a solid number here. And remember, what we're talking about is just whatever function we have. If we go from a to b, then it's going to be the total displacement of all this area right here from a to b. Well, what we can do is actually think about the definite integral as a function of x now. And so we're actually going to get a function that's going to give us this definite integral. Now what you'll notice, a couple things change here. One is we're going to use a different variable. We're going to use a different variable like t. So this is now a function of t in here, and we want to find the definite integral. Now we're going to go from a to x. So what's interesting about this is now this is a constant, but it is a t value. Okay, so it's a value of t. And what happens is the x, this is a variable, but it is also a t value. Okay, so it can get a little confusing because we're mixing the x's and whatever, but basically it's a variable and it can go in for the t value. And what it allows us to do then is kind of have this function, wherever this was, and we can start it at one place, and then we can accumulate the area to any x value. And so this now becomes variable where this goes. So it can be there, or it can be here, or here, or here, or here. And so depending on where the x value is, we can just substitute that in. We're going to substitute whatever that x value is right here into our definite integral function, and it's going to give us that area to whatever x value we want. Now, what we call that, the function capital F at x equals the definite integral from a to x of f at t dt. This is actually called an accumulation function. So it's going to tell us how much area, displaced area, is accumulated from whatever a value to whatever x value we want. And so it accumulates the area under the curve y equals f at t. All right, so let's take a look at example 1. It says find capital F as a function of x and evaluate it at the given x values. So we're going to say capital F at x is the definite integral from 0 to x of the square root of t with respect to t. And after we do that, we're going to use that function to find these values here at 0, 1, 2, 3, and 4. Now, what we're trying to do here, Desmos can actually do. So here we can see our function is the square root of x, and we're just going to call that f at t. And we're going to say capital F at x is that antiderivative from a to x. Now, in this case, we're going to go from 0, and we're going to change that b. Well, at 0, well, we don't have any area there. At 1, we can accumulate it, and we see it's about 2/3 there. If we keep on going, we can accumulate all the way to 2. So that would be the accumulation there. And so you can see that capital F function is actually calculating these definite integrals for us. And so it's kind of nice. If we go to 3, we can see it right there. We can see 4, so on and so forth. So what we want to be able to do is figure out what is that accumulation function. All right, so first off, we want to actually find the antiderivative, and so I'm going to change this to be 0 to x t to the 1/2 power. All right, that way we can solve this a little more easily. And so we're going to raise the power 1. That'll go to the 3/2 power. And we're going to divide by the 3/2, which in this case we're going to multiply by 2/3. That'll make it a little bit easier. And then we want to evaluate this from 0 to x. So just like we did with the fundamental theorem of calculus there. Now what we're going to do is apply capital F at B minus capital F at A. And so we're actually going to plug x into t first. So we're going to get 2 times x to the 3/2 over 3, and then minus 2 times 0 to the 3/2 over 3. Okay, so you can see we plug the x in there rather than an actual number. X is representing any number. Now when we simplify this, what you're going to notice is when you plug 0 in there, that's not going to equal anything, and it will always completely cancel out. And so what we're really left with here is 2x to the 3/2 over 3. Now this is my capital F at x. So whatever I plug in here for x, that's going to be our definite integral from 0 to that number. Okay. So for instance, if you plug 0 in, you're going to get 2 times 0 to the 3/2 over 3. And that's going to equal 0. Now when we look at our accumulation, right, this is just happening 0 to 0, and so we should expect 0 area. Now if we do this at x equals 1, we'll have 2 times 1 to the 3/2 over 3. Okay, and so now we're going to go all the way to x equals 1, and we're going to accumulate all of this area right in there. Okay, so this actually ends up being 2/3, which is about 0.66. Now if we go capital F at 2, we're going to add 2 times 2 to the 3/2 over 3. Okay, so now this is going to go all the way from 0 to 2, and we're going to now get all of this area in there. So this is going to calculate, I'll just give you the decimal, this is about 1.89. If we went all the way to 3 now, we'll have 2 times 3 to the 3/2 over 3. And when you calculate this, you get 3.46. And again, that's 0 to 3. And it's going to give us all of this area now. Okay. And one last one, we'll do all the way to 4. So we'll have 2 times 4 to the 3/2 over 3, and that is about 5.33. Okay, so again, we're going from 0 all the way up to 4, and that's going to accumulate all the area from 0 to 4. Okay. So it's just a really convenient way to create an accumulation function that will accumulate for any x value that we want to do. All right, we'll try it again here with another example. So we have the definite integral from 0 to x of negative t squared plus 2t with respect to t. And then we're going to want to find all of these right here. Now you'll notice as we go and we have a function that falls below the curve, the x-axis, that this area then becomes negative, and so we actually have the displacement of the area for our accumulation. So let's give it a try here. So we want the antiderivative, so it'll be negative t to the 3rd power over 3, raise the exponent 1, divide by that new exponent, and then plus 2t squared over 2, and we evaluate that from 0 to x. Well, we'll simplify a little bit here. So we want to do 2 divided by 2, and we'll get just t squared there from 0 to x. And so we know we can plug in our x first, so we'll have the opposite of x cubed over 3 plus x squared. Now when you put 0 in, well, we're going to be subtracting that, and you're going to see that it does 0 out. So we don't have to worry about that part at all. And so now we just have capital F at x is equal to the opposite of x cubed over 3 plus x squared. And now we're going to go ahead and find these at 0, 1, 2, and 3. Well, at 0, we should get 0 because we're starting at 0 and going to 0. And notice that that is the case if we plug in 0 here. So the capital F at 0 does give us 0. Capital F at 1 means we're going to plug 1 into the accumulation function. And this looks like we're going to get 2/3 here. And capital F at 2. So we're going to have negative of 2 cubed over 3 plus 2 squared. So we get negative 8/3 plus 4. And so that is negative 4/3. And finally, capital F at 3. We're going to have the opposite of 3 cubed over 3 plus 3 squared. And so negative 27/3 plus 9, hey, that's negative 9 plus 9, and so that does equal 0. All right, so just again, a real quick way to calculate these antiderivatives at all of these different x values. All right, let's just do one more example here, practicing this. So here we have capital F at x is equal to the definite integral from 2 to x of t squared plus 3t minus 1. We want to evaluate this at x equals 2, 5, and 8. Okay, so we'll get our antiderivative using our power rule. Okay, and notice when you antiderive this, you're never going to get a constant here. It just doesn't work because everything has to go up a power. Now this is going to be at from 2 to x. Now in this case, we're not starting at 0, so we do have to calculate what's happening at 2. So we're going to plug in x first. So we'll have x cubed over 3 plus 3 times x squared over 2 minus x, and then we're going to subtract what's happening at 2. Okay, and so in this case, it's going to be 2 cubed over 3 plus 3 times 2 squared over 2, and then minus 2. Okay, so we get x cubed over 3 plus 3x squared over 2 minus x minus, and this turns out to be 20/3. Okay. Now, one thing we can do with this is actually use a table of values. All right, so I'm going to go ahead and just put my accumulation function into Desmos here. So we're going to have x cubed divided by 3, and then plus 3x squared divided by 2 minus x, and then minus 20/3. And then I'm going to change this into a table. And now I can just put in the x values that I'm looking for. So I'm looking for 2, I'm looking for 5, and 8. And so really quickly and easily, I can determine capital F at 2 is 0, and we expect that because 2 to 2 is 0. Capital F at 5 would be 67.5, and capital F at 8 is 252. All right, so now we want to take a look at the second fundamental theorem of calculus. And basically what we're saying here with the second fundamental theorem of calculus is that the derivative undoes the integral. The derivative undoes the integral. So here we have it. If f is continuous on an open interval containing a, which is just a number, then for every x in the interval, the derivative of the definite integral from a to any x value of f at t dt is equal to f at x. And so what you're going to notice here when you take a look at this is if we substitute x in for all these t's, notice when we evaluate at a, that's just going to give us a constant number. When you take the derivative of a constant, it's gone. Okay, and so all we're going to really be left with is the derivative of the antiderivative, which is the original derivative at x. All right. Now, one thing you will note here is that when you see f at x here, and we're just plugging x in there, that dt really becomes dx over dx because of the chain rule. And that equals 1, and so it's not really shown here as being anything, and that's why you only see the f at x. But it will matter when this x up here is not just an x. All right? So the first fundamental theorem of calculus says that integration undoes differentiation. The second fundamental theorem of calculus goes the other way. It says differentiation undoes integration. So taken together, they complete the notion that differentiation and integration are actually inverse processes because they work both ways. So let's go ahead and find each of these derivatives here. So yeah, we are finding derivatives, but we're finding derivatives of antiderivatives. Okay, and what that means is it's actually going to cancel each other out. And so it's actually a little bit easy to do this. Basically, what you're looking for is a number as the lower limit of integration. It can be any number, 0, 2, 10, -7, whatever, but you're looking for a variable in the upper limit of integration. Now what you do is you just take that variable and you replace it with t here and here. And so what you're left with is the derivative of the integral goes away, and you're just left with the square root of x squared plus 1. Now because it's just dx, the derivative of x with respect to x is just 1. And so this is your final answer. All right, so we can even do something like tangent. We've never found the antiderivative of this before. Tangent to the fourth, yeah, it could be pretty tough, but it doesn't matter because we're taking the derivative of the antiderivative, okay? And so those are gonna undo each other. So again, we're just gonna take that x and plug it in for t here as well as here. And that will undo. And so we're left with tangent to the fourth of x. Now the dx is really just going to be dx over dx because we're taking the derivative there. That equals 1, and so we're done. Now, when the upper limit of an accumulation function is a function of x rather than just x, we have to make a u substitution and then use the chain rule. So this is what I was meaning. Now we have just a constant as the lower limit, but the upper limit is some function of x. And so what's going to happen in this case is you're going to end up substituting it in for t, but then you're also going to have to put it in here. And so what happens is in the one place, we actually get this g at x going in right there. And then this is going to be that g prime at x. So the dx over dx is now the derivative of g at x with respect to x. So I kind of like to use this over here a little bit better. Think of this g at x as just some other function u, and now the u is going to go in for t here and here. Those cancel out, and you're left with f at u times the derivative of u. So let's give this a try here. Note the directions. It says find the derivative of each capital F. So we are finding the derivative of an antiderivative. Okay. Now, what you got to look for? You have an antiderivative here. It starts at a constant, pi over 2, and then it goes up to a function x cubed. And so what we want to do is we want to substitute it in for t as well as the t in dt. And so what this is going to be, well, I guess we shouldn't show it this way. We would show it something like this, where we're trying to find capital F prime at x, which is the derivative. So this is the derivative of the antiderivative, pi over 2 to x cubed, cosine t dt. So what tells us to plug it in really is when you have the derivative on both sides. So you could do something like this, and that works as well. All right, at any rate, let's go ahead and substitute our x cubed in for our t. So we'll have cosine of x cubed, and then times the derivative of x cubed. All right, well, the derivative of x cubed is 3x squared, and so I'm going to rewrite this as 3x squared times cosine of x cubed. So we really still have to use the chain rule because we're taking a derivative, and you always use the chain rule. So this is how that works out. Let's try another one here. Again, we're trying to find the derivative of capital F at x. So if we want to find the derivative, we'll just take the derivative of both sides. Then the x squared is going to get replaced in for the t here and here. So we're going to be left with 1 over x squared squared times the derivative of x squared. Well, that's just 2x, and then x squared squared is x to the fourth. And finally, we can reduce this. So x divided by x to the fourth will just be 2 over x cubed. All right, in our last example, it says evaluate the derivative with respect to x of the definite integral from 5 to x squared of the square root of 1 plus t squared dt. So again, we're taking the derivative of the integral, and so you don't have to worry about how complex the function is right here. It doesn't really matter because we're just substituting. The tougher part is taking the derivative of whatever function is in the upper limit. All right, so hopefully they're not too hard. This x squared should be no problem for us. So again, we want to take that x squared and plug it in for t here and here. And then the derivative cancels out the integral. And so we have the square root of 1 plus x squared squared times the derivative of x squared. So we'll simplify just a little bit here. 1 plus x to the fourth times 2x. And again, usually we're going to write that 2x out in front. 2x times the square root of 1 plus x to the fourth. All right, so that is the second fundamental theorem of calculus, and basically how to take the derivative of an antiderivative. It undoes itself. All right, thanks for watching. Have a good one.